Hello everyone, welcome again in Eng-Man YouTube channel. So in this video, we will continue our learning on CO2 sequestration modeling with CMG software, and we used a gem to simulate the CO2 sequestration. And in the last episode, we have run the gem for the case of this one, CO2 injection, and we enable the hysteresis trapping as well as solubility trapping. Okay, so here we have the .sr3. The extension is sr3. So I will drag this file and put on the results, and we can visualize the results, which is the result from the gem computation. Okay, and later on we can also compare it with the result from the case of only solubility trapping with, only hysteresis or residual trapping without solubility trapping. Okay, so let's check the result. Okay, so this is the file, CO2 injection underscore hysteresis and solubility. So of course, in this file, in this case, we already include the structural trapping, of course, and we also enable the hysteresis trapping. And the new thing is here. The new thing here is the solubility trapping. Okay, so let's check. This is the aerial view or two-dimensional view. Okay, this is the aerial view, IK 2D view, and JK 2D view. I'm going to go to here, and this is the location of our CO2 injector. Go to display. Okay, we are currently, by the way, looking at the 3D view, and we can visualize many parameters, but I'm interested in, let's check the gas saturation first. Okay, so let's just click on OK. So you can see we inject CO2 here, and the gas saturation increases significantly at the top. Of course, due to buoyancy, CO2 will move up. Okay, CO2 will move up to the top section of the reservoir. Okay, we have very long period of CO2 injection, or CO2 injection plus observation. So you can see this is a very good case, so that we can monitor what happened after 100 years. And I don't know, let's just wait till the end of the simulation. Okay, and we can also switch to, for example, let's check the pressure. What happened to the pressure? Okay, seems like no change. Yeah, because the the scale also you need to adjust. But let's check now the water mole fraction. You see there, right? So here, because we enable solubility trapping, now water can be dissolved into, now the CO2 can be dissolved into the water. So water now will contain CO2, and we represent the fraction of the CO2 inside the water by this parameter, water mole fraction. Okay, and of course now water now has CO2 inside it. CO2 now is dissolved within the water, and the water that contains soluble CO2 will have higher density. Okay, that's why CO2, that's why the shape is like this. Okay, or maybe it's better if I also show you the water mass density here. Okay, so water that contains CO2 will be heavier. That's why here at the top, you see water goes down. It's like raining, right? Because now here right here, water will go down because now it's denser, it's heavier because it contains soluble CO2. Okay, so what's the, let's play with property filter, maybe maximum to be, let's say minimum. What happened? Right, it's like this, the shape is like this. Let's go back to 900. Okay, maybe, okay, okay. And what else? We can also go back to water mole fraction, right? Still, we are still calculating. It's very good. The CO2 injection has been stopped, by the way. So we just wait and observe what happened to the subsurface. Okay, now we stop at January 1st, 2200. Okay, so you can see it's beautiful. Water mole fraction. I mean the CO2 mole fraction inside the water. Okay, and yeah, of course, water mass density because it's heavier. Okay, I'm going to make a distinction on the coloring. Let's say, can I switch the color? No. Oh, sorry. Yeah, sorry. Yeah, you can play with the filter, but actually I don't want to use filter, by the way. I want to adjust the color. Just adjust the color. Okay, let's say it's all right, and then this should be, let's say, just to make this distinction. All right, you can see RGB color or HSV color, intensity if you want, radiance. Okay, seismic, temperature. But let's go back to CMG coloring. Okay, if you want to make it discrete. Okay, so you can see, so this is what happened to the subsurface if you enable the hysteresis trapping and solubility trapping, water mass density, and then what happened again to the gas saturation. So it's like this, the gas saturation. Still you have CO2, all right, at the top, okay? Because again, some CO2 is lighter than the water, so many of the CO2 will be at the top, okay? But there are also other CO2 that will be dissolved inside the water, okay? And even go down to the bottom of the reservoir along with the water. Okay, so suppose now I want to compare it with the case where only hysteresis trapping is enabled without solubility trapping. So what can we do? So let's go back to our model. Okay, so let's find the case CO2 hysteresis. Do I have CO2 hysteresis without, oh, this one, CO2 hysteresis, but without solubility. So I will drag it again to the results, or maybe what I need to do is actually add file here. Okay, add file. Okay, so let's drag it as well here, CO2 hysteresis, and I will drag it there. Then let's touch this one. Okay, so now I have two cases. The this one, the left one is hysteresis plus solubility, and the right one is only solubility trapping. Okay. Okay. Can I squeeze it a little bit? Okay. All right. And then for the display, for this one, let's check the gas saturation. Okay. It's good if we start with gas saturation. Okay. And move it a little bit. Okay. CO2 injector there, CO2 injector there, and let's play. Okay. Looks similar. Okay. But I'm not sure. I think it's, it's brighter there or not. It seems that CO2 in the case of hysteresis only, CO2 at the top propagates farther. Okay. It already takes greater distance from the well compared to the left case, hysteresis plus solubility. It makes sense because on the left, you also have another trapping. You also have, solubility trapping that somehow, restricts your CO2 to move farther because it has more traps, which is the solubility trapping. Okay. So you see, even from gas saturation, you can see the difference between the two cases. Okay. In the case of hysteresis only, CO2 at the top, CO2 plume can move faster or and and farther, okay, compared to hysteresis plus solubility. Okay, we can switch to, of course, this is interesting, water mass density. Of course, in the right case, we do not enable the solubility trapping. So there will be no CO2 inside the water. There will be no CO2 dissolving into the water. Okay, so the water mass density will not be changed on the right case. Okay, but on the left case, you enable solubility trapping, so CO2 can be dissolved into the water. Of course, if you switch to water CO2 mole fraction inside the water, nothing happen on the right case. Okay, because the water will not contain CO2. There is no CO2 being soluble inside the water. Okay, different from the left case. So you see, this is very important thing about having ability to model your trapping. Of course, all the model can can simulate the structural trapping, of course, right? But you need to enable hysteresis trapping, but you also need to enable solubility trapping. Okay, that's this is where the software plays a very important role on, you know, advancing their software in such a way that we can have solubility trapping. And later on in the future, we will also learn about mineral trapping. Okay, and also you need to know that solubility trapping is not a single, a single model case. At least we have two theories or two approaches in modeling solubility trapping. Later on, after this, we will try another approach, another modeling, but still in solubility trapping. But for now, we will just concentrate on looking at what happened. What's the difference between hysteresis trapping and hysteresis plus solubility trapping? And we can actually compare it with no hysteresis trapping. Okay, so let us go to the input again or data source, and let's add files. And I'm looking at CO2, this should be this one. So this is the base case even without hysteresis trapping. So click on open. Okay. All right, so now we have three cases. I'm just going to drag it also there. We should already have three cases, hopefully. All right. Let me extend. Okay. Okay, so right, doesn't matter. Let's go to display. We are currently looking at the pressure. Okay, we can go to the initial time. Or maybe, yeah, just go to the, we are now at pressure, pressure, and pressure. Or maybe better, gas saturation. Okay, let's play. Okay. So on the left one, we have hysteresis plus solubility enabled. And at the right one, we have hysteresis only enabled. And at the center, I have the base case. No solubility trapping, no hysteresis trapping. And of course, you can see in the center case, CO2 will move up very easily just due to buoyancy. Okay, no additional CO2 will be trapped by hysteresis, by the, by the capillary pressure and by the relative permeability phenomena, because there is no hysteresis trapping, there is no residual trapping at the center. But at the right one, you have, hysteresis trapping. But in the left one, you have hysteresis also and solubility trapping. Okay, so this, emphasize the importance of having the ability to model your trapping properly, including the structural trapping, of course, residual trapping, and solubility trapping, and lastly, hopefully we can cover the mineral trapping. So there, all the CO2, or maybe the majority of CO2, will move up at the center case. Okay, move up and then just extend, okay, due to structural trapping. And at the right case, you have some CO2 trap, the yellow one, right? That's because CO2 trapped by hysteresis trapping. Okay, some residual CO2 is trapped inside the pores. And on the left one, you have hysteresis or residual trapping, but you also have some CO2 being dissolved into the water due to solubility trapping. Along with it, we can also model the water mass density. Okay. Nothing happened in the center, nothing happened in the right one. Why? Yeah, because no CO2 being soluble into the water. And of course, the same thing with CO2 mole fraction inside the water. Okay. It only appears on the left one. Okay, so what else? It's very, very interesting. Okay, so this is the gas saturation below the critical gas saturation. So it's like this. Hysteresis dynamic trap gas saturation. You can see. All right. And molality of CO2. Okay. Yeah, we have molality in the left case because it's now CO2 is dissolved into something, and the something is water. So we can represent the molality of the CO2. It's like molarity of something. Okay, it means the molecular mole per volume for molarity. Okay, all right, and then yeah, again, gas saturation. You see, and gas mole fraction CO2. Okay, it's another thing. So you see some CO2 is actually at this section. Okay, but the majority will be at the top. Okay, but many CO2 go down to below, I mean to the bottom of the reservoir along with water. Okay, so that the integrity of the trapping at the left case is better because now CO2 goes down to the bottom. Okay, so it will have smaller chance to break to the surface. Okay, later hopefully we can also learn about mineral trapping, and also we can also go to time series. Okay, time series, and I'm going to go to special history. Let's see, for hysteresis plus solubility, special history, I want to know the CO2 as aqueous ions. Okay, no ion, no ionized CO2, CO2 dissolved there. Okay, because now you have CO2 dissolving into the water. So I want to know CO2 in gas. No. Okay, no problem. In liquid, no. CO2 as mineral, no. CO2 supercritical, yes. Okay, so now CO2 is in the supercritical phase and CO2 being trapped there. Okay, so let's compare it with CO2 injection hysteresis without solubility. I want to know first the CO2 dissolved. Add to new plot. No. And then CO2 trapped at curve there. Okay, so I have CO2 trapped, this one, without CO2 being dissolved. But let's check with CO2 hysteresis and solubility trapped at curve. All right. So how do I want to uncheck this one. Okay, so now I can compare CO2 trap here for the hysteresis plus solubility trapping, and this one, CO2 trap, okay, in, hysteresis trapping only. And yeah, we can also show at the same time CO2 dissolved from hysteresis plus solubility trapping at curve. Okay. So you see, CO2 trap. This is actually CO2 trapped by hysteresis trapping. Okay, this light purple dashed line, it's CO2 being trapped by hysteresis trapping. Okay, and yeah, I mean by hysteresis plus structural trapping, I mean, right? And this one is now CO2 being dissolved. So CMG wants to, differentiate CO2 being dissolved and CO2 being trapped. In reality, a state of this being dissolved is also a trapping, right? So CO2 dissolved is actually CO2 being trapped as well. But this is just a distinction just to differentiate. So we can see CO2 being trapped means CO2, so a free CO2 being trapped by structural trapping, and residual CO2 trapped by hysteresis trapping. So it's reasonable why in the case of hysteresis only, it has CO2 trap greater than CO2 trap in this case. Because in hysteresis plus solubility trapping, you have another form of trapping, which is dissolution. And it is represented by this red line. Okay, and in CO2 base case, let's check the CO2 trapped. Okay, so here the the base case, the CO2 being trapped is the least compared to the other two cases. So you see the ability to calculate the hysteresis trapping is also is actually very important, because the difference, let's just compare the hysteresis versus the base case. You see the difference is huge. Okay, because now here we have residual trapping. Residual trapping is very significant. in terms of amount of CO2 being dissolved, okay, compared to structural trapping only. All right. Okay, now I want to show this one, of course, and this one. Okay. So yeah, and let's see. Let's just compare the CO2 supercritical in 3 cases. Okay. You see this hysteresis plus solubility case will have sort of less CO2 supercritical. Why? Because now CO2 is transferred into the water. Okay. No longer free CO2 in supercritical state. Now CO2 is dissolved into the water. It's no longer, free CO2 in supercritical state. But in the case of base case and hysteresis trapping only, they are the same. Okay. All right. I think that's all. I can go back to here. Okay. So now we have calculated the hysteresis and solubility trapping, and we compare the 3 cases. Hopefully in the next series of video, we can also learn about the mineral trapping. And I think I'm going to exercise as well for another approach for CO solubility trapping. Okay. Until then, see you later. Thank you so much for watching. And again, thank you so much.